First of all, for those of you who are watching on YouTube, some apologies. I'm going to be walking away from my laptop to do some demos. I'll talk loud and hopefully you'll hear, but you won't be seeing what's going on, but I'll try and describe it. Anyways, let's begin. We're going to be talking about Newton's laws. Isaac Newton was a scientist. We're going to be talking about why he is so revered. Kinematics, which is displacement, velocity, time, that's the study of how things move. We're now going to look at dynamics, or forces. This is the study of why things move. So we need to start out by giving you a definition of a force. You know what? A force is a push or a pull. That's a terrible definition for a physicist. A physicist would say that a force is an interaction between two objects on the quantum level when they exchange left. We're not going to dive down to the quantum level all the time, but I am going to start out by pointing out, Camille, everything, almost everything I'm teaching you in this unit, again, is going to be wrong. But if you zoom out, it works pretty good. Okay? Is force a vector or a scalar? Does it matter which way you push on something? Let's find out. Lyle and Aiden, can you both stand up, please? Aiden, can you stand right here? Lyle, can you stand on that side of him facing me? Aiden, facing back. Lyle, stand right here. Facing Aiden. Push. Both hands on his shoulders. Push. 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 Stop. We're going to do the same experiment, but I'm going to change my pushing direction. Same thing. Stay where you are. No. Push. Oh. Does it make a difference which direction I apply the force? Do we get a different result? No. So that's kind of Captain Obvious, but force, vector or scalar? Does it have direction? Yeah. It's a vector. Circle the word vector. It very much matters what direction the force is in. What would be a good symbol to use for force? Capital F. Not lowercase. Lowercase f is frequency. And I think I've mentioned we don't have enough letters in the English language, so we got to be careful. Units. Force is measured in newtons. Symbol or abbrev, capital N. Named after Sir Isaac Newton. One of the things we're going to talk about then is finding the net force. What do I mean by the net force? Well, if I push with 5 newtons right at the same time as I push with 2 newtons right, if I wanted to write that as one single force, how could I replace that with one force? Direction? To the? Yes. What if I push with 5 newtons to the right and 2 newtons to the left? What's the net overall force the same as?
3 newtons right.
So it's not exactly addition. In fact, I think, if I'm being really technical, Parker, here's what you did. You said, I'm going to let the larger force be positive. I'm going to let the smaller force be negative. And I'm either going to go 5 plus negative 2, or easier, 5 minus 2, 3 is my net force. Ooh, what's the net force in this question? As a number exactly? A net force of 0 is a hugely important situation. If you know the net force on an object is 0, you'll learn later you can make a whole bunch of assumptions about that object and you'll know you're correct.
Wow.
What's the net force here? This is physics 12. In physics 12, we're going to go 2-dimensional. In physics 11, the most we'll do is 1 dimension and letting one way be positive, one way be. Okay? In physics 12, now for those of you who are wondering, how do you add those together? You add them tip to tail. The answer is actually 6 plus 3. That's the net force. And if you do the Pythagoras and the trig, that's the answer. If you take physics 12, you'll get far better at SOHCAHTOA trigonometry and Pythagoras. In fact, you'll probably get about as good as that as you're getting at formula manipulation this year. You'll reach the point where one line and your calculator and you're done. And that's my goal in physics 12, because anyways. We need to talk about Isaac Newton. So Isaac Newton lived 1540, 1550, 1560. And you can make an argument that if you list the top 5 scientists of all time, Newton is on the top 5 list, maybe at the top. If you list the top 5 physicists of all time, Newton is on the top 5 list, maybe at the top. If you list the top 5 mathematicians of all time, Newton's on the top 5 list, maybe at the top. He's the only person that I know of who's on those lists. Newton overturned 2,500 years of bad physics. So Aristotle was a Greek scientist who dominated physics at the time. Here's what Aristotle wanted to explain. Watch. He wanted to explain why is it that if you take a ball and you roll it on a flat surface, the ball will slow down and come to a stop. Now, I'm going to give you Aristotle's explanation. It's garbage. But if you listen close, you'll hear that George Lucas stole some stuff for Star Wars from Aristotle. No. So yeah, Aristotle said that all energy, all life contains an energy force. In fact, he used the term force, not in the sciencey term. It's where George Lucas stole the idea of the force from. He said that energy, that life energy, comes from the earth. So, for example, plants grow in the earth. Cows get their energy from the plants by eating the earth, by eating the plants. Where do the plants get their energy from? The earth. You get your energy from eating the cows, which got its energy from eating the plants, which got its energy from the earth. That's why you turn into the earth when you die, because the earth wants its energy back. And so he would say this: when you lift an object up, the reason it falls is the earth wants its energy back. Not gravity. Oh, and when you roll an object on the ground, the earth is leaching that energy out slowly, and that's why it slows down and comes to a stop. That's not a bad explanation. Well, garbage. That's not a bad explanation. And for 2,500 years, that's what was taught. Isaac Newton came along and said, no, I can explain how everything in the universe moves with 3 rules. In 1580, 1590, before we even really invented hot air balloons, he was anticipating how outer space would move. I'll give him full props for that. When Isaac Newton was in college, he was an okay student. He was at Cambridge. When he was in college, the Black Plague came to London. And because he was of the aristocracy, he had some money, what you did back then when the plague came to London, you went and lived in the country and let all the poor people die off. He became what we call a gentleman farmer. That doesn't mean he was picking up a shovel, or he was wandering the fields, ordering people what to do. And in that year, you can make an argument that no human being before or since has thought as much, has aha'd as much as Isaac Newton did in that one year. During that year, he invented the calculus because he was stuck on a math problem. During that year is when he started to realize that white light is made up of all the colors of the rainbow. That is not actually a pure light. During that year, he formulated his thoughts on gravity. And, Jaden, during that year, he came up with his 3 laws of motion. Now, what are they? Here's the first law. Newton's first. It's often called the law of inertia. Here's what Isaac Newton said. If all the forces are balanced, the fancy phrase, the net force is 0, like that one example on the previous page, an object will either remain at rest, if it's already at rest, or move in a straight line at a steady speed. Fancy phrase, if the net force is 0, then A must be 0. What does A stand for, boys and girls? Okay. So this ties into what we've already learned. If an object has balanced forces, if the forces on an object are balanced, it cannot be accelerating. Now, there's 2 ways to not accelerate. If you're stopped, you stay stopped. If you're at rest, you stay at rest. Or if you're moving, you keep going in a straight line at a steady speed, you don't turn, you don't speed up, you don't slow down. It's often phrased, objects at rest tend to remain at rest, objects in motion tend to remain in motion, which is confusing. Alex, if the forces are balanced, A is equal to what? 0. Oh, and it works both ways. If you notice that an object is not accelerating, the forces must be balanced. So it's a rule that works in both directions. If forces are balanced, A must be 0. If A is 0, forces must be balanced. Which means if in your picture the forces aren't balanced, you know you're missing a force. Newton's first is hugely useful. If an object is accelerating, changing its speed or its direction, there must be an unbalanced force acting on an object. The net force cannot be 0. So if the net force is 0, you can't be accelerating. If you are accelerating, the net force cannot be 0. I'd like you to imagine you're the passenger in a car sitting in the front seat, passenger seat, and the driver makes a sudden left turn. Your body wants to keep going in a straight line at a steady speed. Now, you think that you're getting pushed to the right. You feel like, oh, I'm getting pushed against the door. Jaden, that's not what's happening. Your body keeps going in a straight line, but the car accelerates that way. It's actually the door pushing into you. It has to push into you, because if it didn't, you would not change your direction. You wouldn't have an unbalanced force. You would keep going in a straight line at a steady speed. Now, it's a bit weird, Jordan, to think, what do you mean an inanimate object pushes on me? Inanimate objects push on you all the time. The way you understand how things move is almost always backwards and wrong. You're not pushing against the door is pushing on you. The door is pushing on you. So I wrote down here, contrary to what your common sense might tell you, you're not being pushed to the right at all. The driver steers the car to the left. Your body, Newton's first, says it wants to keep going in a straight line at a steady speed. And the only way to make it accelerate, in this case change direction, is for an unbalanced force to act on you. The door pushes on you. Or your seatbelt pulls you in. Okay? As a rule, next page, any object tends to continue moving with whatever speed and direction it currently has. Oh, this includes 0 speed, of course. So if it's at rest, it'll stay at rest unless you apply an unbalanced force to it. When your driver accelerates the car, this explains why your body is a backwards accelerometer. Your body wants to stay at rest. How do we accelerate you forwards? There has to be an unbalanced force pushing on you. What pushes you forwards when the driver accelerates the car?
Right.
The chair, the seat, the back of the seat. Now, you're not used to having an inanimate object push on you, so you think, I'm getting pushed against the seat. No. You stayed where you were. The car pushed you forward. Got to think carefully here. This tendency of all objects with mass to resist a change in their state of motion is given a special name. We call it inertia. That's why Newton's first is often called the law of inertia. Every object in the universe that has mass has inertia. One way you can think about inertia, if you measure an object's inertia, you're sort of measuring an object's stubbornness, its unwillingness to change its motion, its resistance to change. So let's go a little Captain Obvious here. Which object do you think has more inertia, a bicycle or a fully loaded logging truck?
Fully loaded logging.
Okay. Because the logging truck has more inertia, it's more difficult to get it moving. That's why they don't leave a green light very, very fast. More difficult to stop it. It needs more distance to come to a stop. And it's more difficult to turn at a corner. How do we measure inertia? We're going to fudge things a little bit here. We're going to measure inertia as an object's mass in kilograms. This technically isn't right, but we'll find out why it's not right when we look at Einstein. It's right as long as you're not going near the speed of light, which we won't be for a while. So more mass means more inertia. In fact, I'm going to use mass and inertia interchangeably. Inertia, or mass, resists a force. In fact, again, you can think of mass as the measure of the stubbornness of an object, how much it will resist a change in its motion state. The more mass an object has, the less willing it is to change how it's moving. If it's at rest, it'll stay at rest. You got to apply a way bigger force to get it to accelerate. This explains why our bodies are backwards accelerometers. Our bodies don't detect acceleration. We actually are detecting our own inertia, our own resistance to force. I always tell a car accident story. I was rear-ended by a semi-truck on the freeway. It was just before the Brunette overpass, and it was stop-and-go traffic. We were probably doing about 60 kilometers per hour, and two cars in front of me, the person hit the brakes really fast. So one car in front of me, the person hit the brakes really, really fast. I had to hit the brakes really, really, really fast. The semi-truck driver behind me had just looked down to grab his coffee mug, and by the time he looked up, he hammered me. The accident had some great physics. I was driving an old 1982 Honda Accord. It was old enough that it still had ashtrays and a cigarette lighter. Many cars don't have that. And what you did back then, because we still had pennies back then, your ashtray was typically full of coins, pennies and nickels and dimes and quarters. You stored all your change there. When I got rear-ended, the ashtray full of coins flew over my shoulder and hit the back seat. No, it didn't. Actually, it stayed where it was because it had so much inertia. My car got thrown forwards by the semi-truck, but the coins stayed where they were. But to me, it looked like they went shooting over my shoulder. No, they stayed at rest, but my car got shot forwards. The coin tray had enough inertia that it stayed where it was. There's something similar when magicians yank the tablecloth out from underneath dishes. I have my own. What's Newton's first law? Newton's first law says objects with mass, with inertia, will maintain their state of motion unless you apply an unbalanced force. So if they're at rest, they'll stay at rest. If they're moving, they'll keep moving. But if you apply an unbalanced force, they must accelerate. I have here a short little video, this shopping cart mishap.
Oh, what's that stack, dude?
Do those objects have mass? Do those shopping carts have mass? Do they have inertia? Yes. How fast are they traveling right now?
Still zero.
They want to stay that way.
No.
That's not my favorite part. If you look at the guy in the red shirt, he's going to make a bit of a calculation, okay? He's thinking, and I'm going to pause the video right here. Braden, can you see the timestamp? What time is it? I'll bet you this guy's coffee break starts at 8 a.m. And he's thinking, what? Can I go for coffee break 2 minutes early and let somebody else clean this up? That's the look of somebody trying to get out of this, right? Subway sleeper. Oh, yeah. So this person is sleeping on the subway. They are traveling to your left. They are moving to your left. Newton's first says they want to keep moving in a straight line at a steady speed. What happened? More specific, in terms of physics, what happened? His head kept going in a straight line at a steady speed because what's actually causing him to slow down? Friction between his pants and the seat that he's on, but that force isn't being applied to his head. And your head is the heaviest organ in your body. It's got a fair bit of mass. It will keep going in a straight line at a steady speed. There's a really neat one in the space station.
Here we are at the International Space Station. We're doing a reboost, right?
So right now, the International Space Station has just turned on their engines. Pardon me?
He is quite red.
Why? You're right. This is a very great, very good observation. Why?
Inertia.
No gravity to pull the blood out of their face. All the astronauts will always look like they have a red face, and they'll also tell you you almost always feel like your nose is stuffed because gravity is what clears your nose out, and everything that you eat tastes like when you have a cold. You know how things taste a bit weird when you have a cold? Okay? Anyways, I'll take your question in a second. They've just turned their engines on. The engines are pointing out of the screen towards you. So they're accelerating towards you. What it's going to look like to us is that the astronauts are moving backwards. They're not. They're staying at rest. Watch.
Now, and we're showing that the space station is actually accelerating away from us. We're going to float in the middle of the cabin, and it started already. We start off, stop, in front of the camera.
You can see
And we get moved.
And you can see they're accelerating too. They're speeding up away from, no. We're speeding up away from them because we're the space station camera. But there's Newton's first. They're remaining at rest because when they lift their feet up, there is no force acting on them. If there's no force acting on you, you won't accelerate if there's no unbalanced force.
The space station's accelerating, leaving us behind.
Yeah, that's what, yeah. Wow. 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 Ooh.
Wow.
That's amazing. I'll do it again.
But by the way, what that means is right now, while the engine is on, if they drop something, down is behind them. The same way for us, down is towards the Earth. They would feel a very tiny fake gravity, not a full 9.8, but they would feel behind them, and things would fall behind them. That would be down. Okay? Oh, inertia beads.
Inertia.
If you're not accelerating, the forces must be balanced. If you are accelerating, the forces can't be balanced. Newton's second law. Short version of Newton's first law. I knew I'd written this somewhere. If an object is accelerating, there must be an unbalanced force. Or if there's an unbalanced force, the object must be accelerating. Now remember, acceleration can mean changing speed or changing direction because acceleration is a vector. I saw Chris Angel do this on his magic show, and I said, no, this is just good physics here. So force is a vector because direction matters. That was my point of showing you that little magic trick there. Off your phone, please. Thank you. How does Newton's first law help explain how seatbelts save lives? Yeah.
Because it acts as like a seat in front of you.
If the seatbelt wasn't there and the car stopped, what would you do?
Keep going through the windshield.
Okay. Applies an unbalanced force to bring us to a stop. Without that, you'll keep going in a straight line on a steady speed. We used to joke, I grew up right when seatbelts became a law. When I was 4 or 5, you didn't have to wear seatbelts in the car. When I was 7 or 8 was when they passed the legislation. But we used to joke whenever we called, what do you yell when you want the front seat? Okay, so our joke was, shotgun, I'll be the first one out to inspect the damage. What we meant was, I'll be the one going through the windshield if we're in a car accident, and on my way past the hood, I'll inspect the damage before I hit the ground and die. Very morbid joke. Hey, why wouldn't you want seatbelts on a motorcycle then? Yeah.
Because if you had a seatbelt on a motorcycle, it'd be like, you want to be like,
So in a motorcycle, you don't want to be strapped to the tumbling wreckage. In a car, you're encased. You're not going to be, like even if the car starts to tumble, you're on the interior. But yeah, for a motorcycle, we don't want to be strapped to the wreckage. So just understanding Newton's first law the law of inertia, we can already start to look at some accident physics and why we build cars and seatbelts a certain way. Newton's second. Oh, no, I'm still got more. Got to remember where I'm going. So, you ready? We don't want to be strapped to the wreckage. Okay? So, how can we use Newton's first? It's really handy if you notice that an object is not accelerating. So, example 1 says this: Manuel weighs 1,000 newtons, and he stands in the middle of a board that weighs 1,200 newtons. The end of the board rests on bathroom scales. Let's assume the weight is at its center. Fill in the correct weight readings on each scale. Huh? What's the total downward force on Manuel and the board? Add it up in your head. What's the total downward force? Sarah, what's the total downward force? Loud and proud. Is Manuel sinking into the ground like quicksand?
No.
Is he flying into you like Superman?
No.
That means the forces must be, I'm looking for a word that starts with letter B, balanced. So, you know what? Gotta be. Has to be. Otherwise, he would have to be accelerating. Now, the reason it's 600 and 600 is because we put all the mass dead center. What if Manuel walks over to the side a little bit? Well, again, what's the total downward force?
1,200.
Are we sinking into the ground like quicksand?
No.
Are we flying through like Superman?
No.
Then forces must be, I'm looking for a word that starts with letter B, balanced. If I got 850 newtons up here, how many newtons must be pushing up here? Has to be. Let's apply this to some bridge design if we're getting into engineering. What's the total downwards force on this bridge?
22.
32 tons. What is the bridge sinking into the ground like quicksand? I hope not. Is the bridge flying into you like Superman? Again, I hope not. That must mean the forces must be, I'm looking for a word that starts with letter B.
Balance.
So if this support is pushing up with 13 tons, what must this support be pushing up with? Has to be. Has to be. That's the power of Newton's first, is you can really, if you're clever, fill in some missing information. In terms of Newton's first law, the law of inertia, how does a car headrest help to guard against whiplash if you're rear-ended?
It doesn't like whoosh.
I got to correct you. Your head does not go like that.
It stops.
Your head stays where it is. Your body gets thrown forwards. I got to be fussy here. Your head does not snap backwards, because if you put a tape measure, you would notice when you're hit from rear end, your head doesn't move behind from where it started from. It just stayed where it was. And so the headrest is what applies the unbalanced force to keep your head with your body. By the way, when you buy your first car, first thing you should do, it's such a minor thing, adjust the headrest. It's a no-brainer, but do that. Okay? So, you know what? Let's just say this. Applies unbalanced force on your head. But again, you remember I said at the beginning, the way you think things move is completely backwards. Parker said, well, your head snaps backwards. No, it does not. It stays where it is. It's your body that gets thrown forwards, but we don't think that way. Newton's second law is the only big equation you're going to get in this whole unit. It's the equation. This tells us how to calculate force. Newton's second law is this: F equals ma. Find that on your green sheet.
Dude, what the heck? What's my name?
Share without making an argument, please.
F equals F. Yeah.
Okay, find where it is.
Yeah.
Okay, F equals ma. You'll probably memorize this one because you're going to use it about 1,000 times in the next couple of weeks. You don't have to, but this one is worth memorizing because you are going to get sick of looking it up. F equals what?
MA.
Everybody, F equals what?
MA.
What does F equal?
MA.
Oh, by the way, what does M equal then?
Math.
F over A. Yes? What's another way to find A? F divided by? So we now have yet another equation for acceleration. And you're going to start to pick up that the concept of acceleration is a pretty important concept in physics. This also means, since force is measured in newtons, it means that 1 newton is 1 kilogram meter per second squared, because if it's MA, M is kilograms, and A is meters per second squared. In fact, Jaden, for a long time, we measured force in kilogram meters per second squared. And then about, I think it was 80 years ago, there's a group, an international committee that names units, and they decided to name this as an abbrev, a Newton, after Sir Isaac Newton. Malcolm has a mass of 45 kilograms. What's the magnitude of the gravitational force acting on him? Huh? What's this question asking me to find? One more word. Gravitational. Gravitational force, you say? Well, F equals what?
MA.
MA. What's Malcolm's mass?
65.
How do I know that that's the mass, even if they didn't say mass? Kilograms. So you do want to memorize that kilograms means mass. What's the acceleration due to gravity? We're not going to put the negative in because that said magnitude. This is how many newtons of force the Earth is tugging down on Malcolm. I can do this in my head. It's going to be 650 take away 13. 637? Yes? Units, it's a force. Newtons. There's your first force calculation. Okay? The Earth is pulling on Malcolm with 640, roughly, newtons of force. That's what's holding Malcolm to the Earth. By the way, gravitational force has a special name. We call it weight. Your weight is not measured in kilograms, it's measured in newtons. We'll do a whole section on that later on. Okay. Cross out the word Malcolm. And, who shall I pick on? Let's go with Denzel. Cross out the word Malcolm. Denzel. Let's assume, Denzel, that your mass is also 65 kilograms. Stand on the table, please. Stand on your lab table. You'll fill this in after. You'll get it from Liz, but stand up on your lab table. What's the magnitude of the upward support force that the table exerts on Denzel? What? So you ready? Draw a little dot. That's Denzel. We call this a free body diagram. We're going to do a whole lesson on this. What are the forces acting on Denzel? What's the obvious one that we just calculated that's affecting all of us? Begins with letter G. Gravity. How big is gravity pointing down? Exactly 637 newtons. Look at Denzel. Is he sinking into the ground like quicksand?
No.
Is he flying at you like Superman?
No.
That means the forces on Denzel must be, I'm looking for a word that starts with letter B.
Balance.
How big must the table be pushing up with exactly as a number? Has to be. Now that's a weird concept. You're not used to thinking that a table is pushing back up on you. It must be. If it wasn't, you would have to be accelerating. So the answer to part I, 637 newtons, how do we know that that force must be there? What law did we use? Why? We used Newton's first, the idea that if forces are balanced, you're not accelerating. You can sit down now. Mummy, I got to stand on the lab table today. We call a diagram like this a free body diagram. And that will probably, in the same way that DFIC was the handy tool I gave you last unit, this unit, you'll often hear me say, this is a job for a free body diagram. Although I tend to abbrev FBD. Phone away, Parker. Put it away completely, please. I'm going to start to take phones away because you're looking at them an awful lot. Yeah.
This is a little bit different, but say like the vehicle is 600 force or meters. Yeah, is that like the force of the car is like applying?
Torque, if you want to figure out the torque, it is the force that you apply times the rotational distance from the center of the pivot. So the units are Newton meters, because this is a distance, it's a radius, but it's actually what's called a cross product. It's a more complicated, I'll come back to that and give you a better answer. Or take physics 12, I'll give you an even better answer because we look at torque. Oh, example 5, let's do some spacecraft. Space shuttle. I miss the space shuttle. It was my spacecraft growing up as a kid. I was 12 years old when I watched them launch it for the first time, and I watched it land live on CNN. It was really cool. The space shuttle has a mass of 2.03 times 10 to the 6th kilograms. It does. If each engine can exert a force of 12.5, what does a capital M and abbrev for? Meganewtons. A, what's the maximum acceleration of the space shuttle? Okay. Ronan, what's this question asking me to find? So I wrote this. I went A equals question mark. And then I said, did they give me a VI anywhere? Did they give me a VF or a T or a D? No. What's this kilograms here? What's that? Mass. Do I have an equation that has mass and acceleration in it? Okay, so I wrote down m equals 2.03 times 10 to the 6th. What's that 12.5? I wrote down F equals 12.5. What's mega? 10 to the what? So I said times 10 to the 6th. And then I read the note. What's the note? I put a 2 times in the front. I'm looking for an equation that has an A, an M, and an F in it. Well, there is one. F equals what? MA. Ronan, get the A by itself, please. So, and I did this now that we're starting forces will be part of your checklist. Liam, when I ask you to find an acceleration, you'll have about 5 different approaches. Make your list, ask what they gave you, and that will guide you as to which approach to use. Ronan, A equals what over what? So it's going to be 2 times 12.5 times 10 to the 6th divided by 2.03 times 10 to the 6th. This is one worth all of you practicing typing in. Probably brackets around the top. Brackets or scientific notation around the bottom. I got 2.4630. Let me check for typos. No, I got a typo. Oh, I got a major typo. The 12, the 1 didn't show up. 12.3?
Yeah. Same.
12.3. How big is 1g of acceleration? You all know this. So this is this is about 1.3 g's, a little more than a g. Units, it's an acceleration. Okay. If you didn't get that, show me later. Oh, question for you. Mr. Dueck. Yeah. That's only about 1.2, 1.3 Gs. But Mr. Dueck, you said the astronauts are pulling 5 or 6 Gs. Are we lied to? Do the astronauts not pull a lot of Gs? B. Why does the maximum acceleration change as the engines burn? Yeah.
First thing, I think I
I'll look at your calculator later. Okay, sorry, but I got to move on. Why does the maximum acceleration change as the engines burn? Yeah, Braden. Let's ignore air resistance. It would still change.
Less fuel.
So what does that mean?
Less fuel.
What?
Less mass. Oh, smart Parker.
As this number gets smaller, but your force stays the same, what's going to happen to your acceleration? Answer. If you divide by a smaller and smaller number, what happens to your answer?
It gets bigger.
Yeah.
Bigger.
So I'm going to write as m decreases, a increases, but I'm going to abbreviate. As m decreases, arrow pointing down, a increases. Do you know when the astronauts pull the maximum G's? Right before they shut off the engines, because that's when their mass is at its lowest. And in fact, they actually have to throttle back the engines near the end, otherwise they would black out. Because I don't know if you've watched a spaceship take off live on TV. It leaves very slowly from the launch platform. And you might have, if you're a nerd like me, thought, that doesn't look like much acceleration. I could handle that. I could. On the platform, no problem. But shortly before engine shut off, I'd be unconscious. I'm not in good enough shape. Is that all right? Why does Newton's second law help explain why a sprinter might want to wear lightweight shoes?
Less mass. Less.
Parker, what?
Less mass.
Okay, let's write down again, A equals F over M. Let's suppose you're an Olympic sprinter and you've lifted weights, you've trained, you can't increase the force from your legs anymore. You've maxed that out. What else can you control? As the shoes get lighter, your acceleration is going to get bigger. I'm a little surprised that they're still wearing shoes. If any of you go into sports science or material science, here's what I think. They should have a liquid rubber latex that you roll on with a paint roller on the sole of your feet. You would then, while it was liquid, step on a tread mold that would be suitable for whatever track you were on, and that rolled on rubber sole would last for one race, and then you would take it off. I'm a little surprised they haven't come up with something like that, because the whole top part of the shoe, that's wasted mass. And especially for the 100-meter sprint, when you've seen the difference between a gold and 10th place is like 0.2 seconds, that's got to make a difference. If any of you come up with that or invent that, patent it, just give me credit. You don't need to give me any money, but just say your physics teacher suggested it as an idea. Yeah.
They use spikes. Or they don't use a tread pattern, they just use spikes.
Yeah, but you could do that with a latex mold as well.
No, I know.
Like you don't need the top. In my mind, the top of the shoe is just wasted mass.
It was latex with the spikes and pull in your feet.
No, you could work. You could easily work. You could work around that, I think. So Newton's first law, the law of inertia. If you're not accelerating, the forces must be. I'm looking for a word that starts with letter B. Balanced. If you are accelerating, the forces cannot be balanced. Newton's second law, F equals what?
What?
F equals what? Everybody, F equals what? That wasn't everybody. Everybody, F equals what? One more time, F equals what? Okay, that's Newton's second. Newton's third law is often phrased as follows. For every action, there is an equal and opposite reaction. I've always found that confusing. My version, forces come in pairs. You know what? If you want to really be fussy, forces come in opposite pairs. If I want to write it mathematically, the force of A on B will be equal to the force of B on A, but opposite. What would be a good, clever way to show opposite without a lot of writing? What would be a clever, mathy way to show opposite without a lot of writing?
Flip of S.
No. What's the opposite of 5?
-5.
How about a negative? People, don't overcomplicate this.
Oh.
Okay? What this means is that all forces are always interactions between two objects. If you had an object sitting in outer space with no motor, no engine, not near any planets, with nothing else touching it in the vacuum of space, it cannot be experiencing a force because forces are interactions between two objects. Forces come in pairs. Some good examples of Newton's third. So Parker, could you stand up, please, my friend? Right here, could you assume push-up position, please? And I'd like you to do a push-up. Okay, go down again. Now push yourself up. Which way is Parker pushing with his arms? Stay there.
Towards the ground.
Direction.
Downwards.
Which way is his body accelerating?
Upwards.
Then it cannot be his arms that make him go up.
It's the ground.
What?
It's the ground that's making move.
Brilliant. Parker applies a force against the ground. Forces come in. The ground pushes back up. By the way, do one again, please. How are they called push-ups? You're pushing down. Can we not agree that the name should be changed to push downs?
Yeah.
By the way, if it was Parker's arms that made him go up, he could lay on this table with his arms in midair and somehow raise his body off the ground just by doing this in the air. It's not your arms that make you go up with a push-up. It's the ground that makes you go up in a push-up. The forces come in pairs. Sarah, could you stand up, please, right here? And I'd like you to pretend like you're about to start sprinting. So just stand here and assume a sprint position, facing that way. Come on, like you're ready. Okay, stop. Stop. Freeze where you were. When you start to sprint, which way are you accelerating? Be obvious. Forwards. Which way are you pushing with your feet?
Backwards.
So it can't be your feet that make you run.
It's gotta be the ground.
You apply a force against the ground, friction pushes back against your feet. In fact, if you're on a slippery, wet field and you try applying too large a force, because now we have an unbalanced force, your foot must accelerate in that direction because forces can no longer be balanced. Or if you can sit down. If you're walking, for example, on ice, how do you, first of all, when you walk, it's not your feet that make you go forward, because think about it, you're pushing backwards. This is why you can't walk on ice, and I gotta be fussy. It's not just the ground, it's a force that we're gonna look at called friction. Ice has no friction, because the ground is still there. It's why you can't walk on ice. It's not because your feet make you. Again, if your feet were all you needed to walk, you could walk on ice just fine. In fact, if you think about how you walk on ice, what you actually do is you go into a controlled free fall. You lean forward and you shuffle your feet underneath your body, and you're fine right now. When are you going to wipe out? I'm not going to wipe out here. When am I going to wipe out? When I try and come to up?
Stop.
Because now I need a force pushing that way to get me to stop, and the ice can't do that. So my feet are going to keep going in a straight line at a steady speed, and I'll go my back. If you're paddling in a canoe, which way are you pushing with the paddle? Think about it.
Backwards.
But which way is the canoe accelerating?
Forwards.
It's not the paddles that make a canoe go forward. It's the
water.
The canoe applies, the paddles apply a force to the water applies the forwards force back to the paddles, and you, because you're holding onto the paddle.
Wow. Yep. That's what.
Yes.
Yeah.
Another really, really nice example, helicopters.
Whoa.
Where's my on-off switch here?
Helicopters don't make sense to me. I get it.
I always have trouble finding the little on-off. There it
You're
is.
telling me 2,000 pounds just lifts into the air.
Okay.
Right.
Oh, did it not recharge?
They're not real.
Yeah.
There we go.
Yeah, you know.
Come on.
It's not real. It's not real.
Okay. Which way is it accelerating right now?
Upward.
Come back.
Come back.
Which way were the rotors applying a force?
Downward.
So it can't be the rotors that made it go up. What did the rotors apply a force against?
Air.
Would a helicopter work in outer space?
No.
This is why we don't use propellers in a vacuum. Would a helicopter work underwater?
Yes.
That's all a boat propeller is. In fact, it's even better underwater because water is so much more viscous than air. I need a massive rotor to lift a helicopter in the air, but a tiny propeller can move a much more massive boat through the water just fine.
Why don't submarines have rotors?
They do.
Yeah. They do have pop.
No.
No, they just use air. It's more. Oh, it wouldn't be very stealthy if you just went.
That's the whole idea about submarine.
Another nice example, tug of wars. Okay? Who wins a tug of war? Well, first of all, if you've ever been in a tug of war, it's not how strong your arms are. What's it come down to? You think about it, you're actually pushing forwards with your feet. And friction between your shoes and the ground is what's applying the backwards force. And if you don't believe me, have a tug of war with one team wearing socks and one team wearing sneakers. Doesn't matter how strong the people in socks are, they're not going to win. The forces come in pairs. Spencer's off his phone.
Yeah. What if you're wearing extreme air pressure socks?
Okay. Can I borrow Jordan and Marley? Can I borrow you two, please? Can you come up here?
Tug of war, tug of death.
So we're going to do a little demonstration to prove that forces come in pairs. Jordan, if you want to stand right here, facing this way. Marley, if you want to stand right here, you want to put both your hands against here. Marley, put both your hands. You're going to push. You apply force. What you're going to do is you're going to read the black scale. That's in kilograms, but if you multiply by 10, that's roughly newtons. So if you get to 5 kilograms, 50 newtons, how many newtons of force? Push as hard as you can. Go, 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 go. Okay, stop. What do you get it up to? 20? 20 kilograms times 10 is 200 newtons of force.
Wow.
Who thinks they can do better? Who thinks they can do more than Parker? Come on up here. Marley's here.
You can't do better.
If I don't do better,
you do better than a woman.
No, he can't do better.
I can't. Is it impossible to do better?
Forces come in.
Pairs.
If the biggest force that Marley can exert is 200 newtons, what's the biggest force that Parker can match with?
200.
Go hard. Now, if he does more than Marley can do, 202, then we have an unbalanced force, and you can see they started to accelerate. And I stopped it before she fell. Okay? Forces come in pairs.
Oh,
Got it. 60.
So,
That's how much Denzel weighs.
how does Newton's third law help explain why it's difficult to walk or drive on ice? What's the force that you need to walk or drive? Friction. Okay? So, no friction on ice, so no pair. And if you don't have the pair, you have to have a pair, an interaction between two objects for a force to occur. I think we're almost done. A couple more. Yep, good.
Can we see the videos?
Yep, I'm going to get to them. Okay. A great example of Newton's third is firing a high-powered rifle. The rifle applies a force to the bullet. Forces come in pairs. What does the bullet do? Applies the same size force to the...
Gun.
Yeah, absolutely.
So it shoots back.
Yep.
That's why when you do rocket, you
It's usually right around now I say, this is, stay off your phones, please. This is terrible gun safety. This is terrible gun safety. But the physics here is pretty good. This is a very, very high-powered rifle. Its nickname is an elephant gun. It's a very high-powered rifle. So one really good example is rifle recoil. Yeah. I can't, louder.
What would happen if running trucks? You don't want
There's a fair bit of kick to it. You'd really need to brace yourself. And I suspect they're using rounds that have an even bigger kick, more gunpowder, more force. Oh, bad physics.
Patrick Frischer is gearing up for his big jump. Wow. And what's he jumping over? This large pile of loose dirt.
I called some of my friends and said, hey, I think I might try this one trip by and see if it's at all possible.
Wow, sounds like he's really thought this through.
I don't think he's gonna do it.
So I have a series of videos that I jokingly call bad physics. What do I mean by bad physics? When you're doing something so dumb that the universe steps in and says, are you kidding me? Bruh. So see if you can spot when the universe steps in, okay?
With friends like these, how could he possibly fail? The amateur daredevil revs up and takes off. Pat is going roughly 60 miles an hour when he hits the dirt with his wheels.
All right, let's talk a little bit here. First of all, the motorcycle applied a force to the dirt. Forces come in pairs. What did the dirt do? Applied a force to the... So the motorcycle experienced an unbalanced force backwards. It's going to slow down. Is Patrick attached to the motorcycle? Patrick is showing us Newton's first law. He's going to keep going in a straight line at a steady speed. Now, you might think this is where the universe steps in. No, no, no. See if you can spot it. When the motorcycle lands on top of him, that's the universe stepping in and saying, dude.
Then his head.
The dirt was real loose, which caused my tires to get in the jump and launch me over the handlebars.
So what does Pat think of his momentous jump?
I know not to do something like that ever again. It was just stupid to begin with. It's still stupid now.
Yeah. I told you, helicopters. So again, a helicopter applies a downwards force but accelerates up. It must be the air pushing it up. This is kind of a neat home build, although also terrifying. This is the world's smallest manned helicopter. I'm going to turn it way down because it's loud. It's a two-stroke engine. Oh, by the way, why does he have two propellers? If he only had one propeller, you ready? The engine applies a counterclockwise force to the propeller. What does the propeller do? Applies a force, and with only one propeller, he'd be spinning in the opposite direction. Now, we get around that with helicopters in two ways. You'll either see helicopters have two propellers, they're spinning in opposite directions, or they have that one long, smaller propeller on the end to do a counter-torque rotation. That's a torque issue, but that's the workaround. If they didn't have that, well, if the engine makes the propeller spin clockwise, the propeller is going to make the engine and helicopter spin counterclockwise because forces come in. So he's got two propellers. They'll rotate in opposite directions. This is a backyard build. It's pretty cool, but also a little bit terrifying.
You put rotors on the tripod. I thought that's what
Okay.
That's so cool.
Now I want you to notice, which way is he accelerating right now? To the left? But which way are the rotors pointing? Pushing. They're applying a force to the right. They're applying a force to the right. The air, forces come in pairs, applies a force to the left on the helicopter. Okay? And it's a pretty easy, the tripod, that's really what gives him leverage to steer. Right? He's got pretty good control. But you'd have to be really careful that you didn't go over too far. That's what would make me really nervous. Now do a Google search. Plans might be online. higher you go, more energy it requires. A thing does not have a large fuel tank, right? And then he lands. Newton's. Oh, here's a clever use of Newton's first to unload a truck.
What about this stupid crook of the
I'm
month?
getting there.
Oh,
Gotta have patience, dude.
I thought it was going in the car.
What's it called? Newton's first.
Calm down.
What's the best way to unload that truck? If you're clever, you can do the same thing that Matt and I did when I yanked the tablecloth out from underneath the big container of water. Yep.
Wow, that is genius. That's a long.
Clearly this truck is rear-wheel drive. This would not work on a front-wheel drive. Okay. Now, there is some force pulling forwards, but those logs have so much inertia that they're not accelerating. Oh, sorry, wrong button.
That guy's a hero.
Stupid crook of the month.
That's insane that he actually did that. Must be terrifying.
Welcome back,
Bad physics. See if you can spot where the universe steps in.
everyone. Finally, it's time for our stupid crook of the month. And this time around, you get 2 stupid crooks for the price of 1. Let's go ahead now and take you right to the video where you can see just how 2 would-be burglars attempted to literally bust into this establishment. You can see crook number 1, the lookout, is handling his assigned task very well, making sure no one is looking, at least if you don't count the surveillance camera. And
So, this guy here is about to throw a rock against the window. The rock will apply a force to the window. Forces come in pairs. What will the window do?
Fly it back from the wall.
what does he get for being such a quality lookout? Knocked out. The boulder
That's not the universe stepping in yet. Wait for it.
his partner used drills him right in the coconut. Now that his cohort has completely disabled his partner, it doesn't even check to see if he's okay. He decides to throw another boulder through the glass. Oops! He too enjoys a brick sandwich.
I'm going to argue that if you had a Hollywood stunt team and a $2 million budget, you could not pull that off in real life. That is the universe stepping in and saying, you're being stupid. I'm going to get your attention. Okay, so a nice example of Newton's third. How does Newton's third law help explain why professional boxers need to wear boxing gloves?
Break your hands.
Yeah, forces come in pairs. If I punch you hard enough to break your jaw is going to apply the same force to my hand. Okay? I don't want to write a big paragraph. Oh, how about this? F hand on face equals negative F face on hand. Right? If I hit someone hard enough to break their jaw, I'm breaking bones in my hand. That's how it's going to work. Also, you could make an argument that the gloves increase the mass, and since F equals what? MA, they might also increase the force. Why do you lurch forward in a bus that suddenly slows?
Because the chair is pushing you forward.
Let's suppose you're standing. So it's standing room only, you're holding the strap, or you're on SkyTrain and you're standing. Why do you lurch forward when the bus suddenly slows? Or why do you lurch backward when it picks up speed? Or do you?
Because you're standing still.
Braden.
Because your feet are kind of touching the ground, so you're still.
Yeah, so if you're already moving, you want to keep going in a straight line at a steady speed, you have to yank at a strap to bring yourself to a stop. Or if you were at rest, you want to stay at rest. That second one, you don't actually lurch backwards. You stay where you are. It's the train that's moving out from underneath you, or the bus is moving out from underneath you. What law is that? Newton's first, Newton's second, or Newton's third? So you do not need to memorize which one is Newton's first, which one is Newton's second, and which one is Newton's third. If you do, you can use that in your answer, or if you haven't memorized them, you could say something like, want to remain at rest, and I would live with that. But if you want to just say the law, drop the mic and walk off, I'm fine with that too. Okay? In the collision below, let's make the one on the left a big moving van, a 5-ton moving van. Let's make the one on the right a little Austin Mini, little mini Austin. Which vehicle experiences the larger force? You know what? We're going to vote. Once again, how high you hold your hand up is how sure you are of the answer. I'm positive, I'm pretty sure. I'm only guessing because Mr. Dewick could make fun of me if I don't vote, and Mr. Dewick will make fun of you if you don't vote. So in the collision below, which one experiences the larger force? Who said, Mr. Dewick, the truck is bigger, it'll feel the bigger force? The truck. 1, 2. Who says, no, Dewick, the car is getting creamed, the car is experiencing a larger force? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12.
It hurts.
Who says, no, they're both the same. 1, 2, 3, 4, 5, 6, 7, 8.
How did we get 22 votes?
So, what's the correct answer?
It's B. It's B.
Why is C correct?
Oh, that's right. Just like Parker and Marlon.
Folks, forces come in.
Opposite pairs.
So you can either write Newton's third, or you can write forces come in pairs. Now, here's the problem. Those of you that picked B are confusing damage with force. Okay? So let's ask, why is it that the car and driver are almost always worse off as a result of this collision? It's not force that does damage. It's acceleration. Parker, what was the equation for acceleration that you came up with when we were looking at the sprinter shoes? F equals what?
F equals what?
Get the A by itself.
No, A. B. F times.
Okay? They both experience the same force. Which one has a smaller mass? So which one will have a bigger acceleration? In this case, deceleration, but which one will have a bigger change in velocity? Okay? The truck will hardly feel it. And so if you're in the truck, in the cab, I mean, you'll feel a bit of a bump. The car will really feel it. Okay? So, oh, I don't want to have, you know what? As M decreases, A increases. And that's one of the things I would say to you in a car accident, it's the acceleration that does the damage. That's one of the other things seatbelts do. They don't bring you to a stop really quickly. Most modern seatbelts slowly bring you to a stop because if they can increase the distance, that lowers the acceleration a little bit. What's your homework?
This.
Look at number 1, please. It says this. Little Nellie Newton wishes to be a gymnast, and she hangs from a variety of positions as shown. She's not accelerating. That means the force is 0. The forces must be, I'm looking for a word that starts with letter B.
Balance.
Okay. So if she weighs 300 newtons, if gravity is pulling down on her with 300 newtons, how big must the spring be pulling up with? Has to be. What about in B? How big must each rope be pulling up with?
150.
I'll let you try the rest of them on your own. The answers are at the bottom of the page. Same for number 2. So your first set of homework, all these questions. Okay? 5 is good. 6 is good. 7 is good. 8 is good. 9 is good. 10 is good. So far I've assigned everything. Then take a look at the section that says Newton's third law. And for some reason it's number 10 again. Don't overcomplicate this. Fist hits wall, wall hits fist. Head bumps ball, ball bumps That's all you're going to write, because forces come in pairs. That'll give us something to discuss next class then. Okay, so you can try all of these.
What is this?
Okay, put a star next to number 11. This is the curveball. With me? Okay? Jade and Liam, be with me here. I'll get back to that, but I'm about to explain a question. Put a star next to number 11. Here you're finding the acceleration. You're going to use that. But B is the tricky part. I'll let you think about it. I'm not even going to talk about it. See if you can look at the answers and figure it out, or figure it out yourself. Okay? Then, Section 2 says, classify each of these as an example of Newton's first or Newton's third. You can just write a big 1 or a big 3. Do you think that these are an example of Newton's first law or Newton's third law? Some of these have more than one answer. So 1 is good, 2 is good, 3 is good, 4, yeah, these are all good. Okay? Then, when we get to, again, Newton's third law, number 1, it says, what is the reaction force to the action force in each of the following situations? If a football player kicks the football 500 newtons up, football pushes 500 newtons, which direction? Down, on the foot. A book pushes down on a desk with 25 newtons, desk pushes up with 25 newtons, because forces come in pairs. Okay. So that's how you do those ones there. And then number 3 is a thought puzzle. I know I'm throwing a lot at you. 4 and 5, and then I've got the answers here. Okay? So I assigned every question. They're mostly conceptual, and we'll talk about these. This is due Tuesday. Your real homework is to get ready for the test. But because I don't see you basically for another lesson until Tuesday, I've thrown a bunch at you.
Monday. Friday.